Okay, so the next thing I want to talk about is how we're actually going to use these Laplace transforms. And I want to discuss that using a very simple example. And of course, we're going to do a lot of these in class, so don't be scared if this is a little bit confusing. But let's take a look at this simple differential equation, f double prime minus f equals negative t. Now in this class, we've typically been using y and x as our dependent variables. So this dE could easily be x double prime minus x equals negative t as well. I used f because our properties have been using f as our function. Now what we're going to do to solve this differential equation using Laplace transforms is we're going to take the Laplace transform of both sides of the differential equation. So that means the Laplace transform of f double prime, the Laplace transform of f, and the Laplace transform of negative t. Now, if we look at our properties, you'll see the Laplace transform of f double prime in there. The way that I wrote it a minute ago was s squared f of s minus little f of 0, minus s times little f of 0 minus f prime of 0. Now the Laplace transform of f is this next piece right here. That piece right there. Now, we just use a different notation for that. The Laplace transform of f, we can also just write as a capital f of s. So that piece is the same as that piece. And let's see, this whole thing is that Laplace transform right there. Now the Laplace transform of negative t, we've done t several times. We know the Laplace transform of t is 1 over s squared, so we just put that negative sign in there and that's what we get. Now you'll notice we have some initial conditions in this line here. Fortunately, we were given initial conditions in this problem. So what we can do is we can plug in f of 0 equals 0 and f prime of 0 equals 1. Okay, so simplifying, we get s squared f of s minus 1 minus f of s equals negative 1 over s squared. Okay, let's take a look at this. So we now have an algebraic equation. And in this algebraic equation, s is our variable. And we have these capital F of s's. Now keep in mind that means the Laplace transform of f, little f. Now little f is actually what we're trying to solve for in this differential equation. Little f is our goal. That's what we're trying to find. So what I propose is solving this algebraically, purely algebraically, for capital F. Which would basically mean, I'll do it in a couple of different steps. But getting all the capital F's on one side of the equation, factoring out a capital F, and before we actually solve for F, I want to do a little bit of algebra on the right-hand side, because I'm afraid this next step might be confusing if I do it all at once. So I'm going to do some algebra on the right-hand side. Common denominator is s squared. So I'm getting s squared minus 1 over s squared. Find a common denominator. Do it in a couple steps if you need to. That should be the right answer. Okay, now we want to divide both sides of the equation by s squared minus 1 to solve for capital F. Now, you'll notice if we do that, we're just going to get some cancellation on the right-hand side, and we're just going to be left with 1 over s squared. Now, what this line says is the Laplace transform of our answer is 1 over s squared. Now, think about it. We have found that the Laplace transform of t is 1 over s squared. So if the Laplace transform of our answer is 1 over s squared, then our answer must be t. So what this line tells us is that f of t equals t. That is our solution to our differential equation with our initial values in there. Our initial value problem has been solved. You could take this answer, plug it in to the differential equation, plug it in, make sure it satisfies the initial conditions, and it does. So that is the simplest example of using a Laplace transform to solve an initial value problem. We took the Laplace transform, we got a function, an algebraic function with f of s in it. We solved for f of s, and then we used sort of our knowledge of the Laplace transforms to figure out what our function had to be. Now this process with this big arrow going around here, this is called an inverse Laplace transform. Inverse transform. It's sort of doing the opposite of taking a Laplace transform. It's an inverse transform. Now, we need to get better at doing these inverse Laplace transforms if we're going to solve differential equations, because things won't always come out to be this simple. So that's what we're going to do in the next section. We're going to get better at finding inverse Laplace transforms so we can solve more of these differential equations. We'll go over this again briefly in our next class, so I'll see you then. We're going to talk more about Laplace transforms, properties of Laplace transforms, inverse Laplace transforms, and we're going to solve DEs using these things.